It's mostly to this hybrid, but mostly online talk. Let's see, got it. Okay, today we're very happy to have Lieke van Son from the CFA at Harvard. Lieke is a final year graduate student. She's also got an appointment at the University of Amsterdam. And
yes.
today we're talking about black hole mass distribution, 30-something solar mass black holes.
Yeah, thank you very much. I hope everyone can hear me all right. Thank you for having me, alas, online. I would have very much loved to be there in person, but as Liam was saying, I'm actually finishing up my PhD, and I have a couple of things that I have to be here to make sure my degree will actually, or my defense will actually go all right in about 2 months from now. So that's going to be exciting. And as I'm nearing the end of graduate school and also inevitably nearing my 30s, I thought it'd be good to talk a little bit again about something that I've been interested in the past, over the past couple of years, my PhD, which is 30-something black holes. So that are black holes with masses in their 30s. And I'm going to go, of course, I haven't done all of this work by myself. This is a lot of awesome work that I'm going to be showing, is also in collaboration with people all over the world, both at the Harvard and CFA in Amsterdam, and people at the CCA New York and in Munich. So a very wide collaboration. But so I'm going to start this talk with my summary and basically skip right ahead to the final conclusion. So I'm going to talk or show you today that I think the observed bump at 35 solar masses is not caused by pair-instability supernovae, which is something that has been claimed and said over the past couple of years. And so if you are known in this field, or if you have been following some of the literature, this might be something of a new thing or a weird thing. If you haven't been following, then let me just take a couple steps back, and I will, throughout this talk, surely explain why I think this is. But before I get into that, even, I want to just highlight very quickly why you should care about these 30-something black holes being caused by this thing called pair-instability supernovae or not. And I'll briefly gloss over this slide, because the implications of this feature belonging to what we call pair-instability doesn't only have impacts or repercussions for what we expect to be the dominant formation of black holes. It also will tell us something about cosmology. It allows for a measurement of the H0 value. It allows us to learn more things about stellar deaths, and even to constrain nuclear reaction rates from all from this one bump. But I will get back to this slide in due time and hopefully make it a little bit more clear at that point. But before I explain all of this, I want to go back and do a little bit of history, basically very recent history from the last 7 years, 8 years already. So the first detection of a binary black hole merger ever, gravitational wave 1509-14, was groundbreaking for many, many reasons. One of these reasons was actually the surprisingly high mass, because from a stellar perspective, a stellar physicist perspective, we hadn't seen any stellar mass black holes with masses of more than 20 solar masses up to this event. And suddenly we have 2 black holes with about 30-something solar masses. Now, the reason that we didn't expect to see such high mass black holes from, at least coming from stars, has to do with the winds. Basically, if you have very high metallicity environments like our galaxy, which is solar metallicity, the maximum black hole mass that you're expected to get is only about 15 solar masses. And this is because radiation-driven winds are very heavily dependent on metallicity. And so high metallicity will give you stronger winds, will give you lower mass black holes. And only in lower metallicities, or even very extremely low metallicities, did we expect to be able to form cores of higher than 20 up to even 80 solar masses. But as time evolved over the past couple of years, we also have seen the catalog evolve. So from the first catalog, gravitational wave transient catalog #1, we've accumulated more and more merging black holes, where this is this beautiful outreach image from the Northwestern group that shows for every 2 dots, depicts one binary black hole merger merging into one bigger black hole. And if you sort these by their masses, you will already very simply from this image start to see that these 30-something black holes are not so rare after all. Even more, we're very much seeing a very, maybe the largest group that we are observing in the gravitational wave observations. Now, there is also a bias engulfed in this, because we are able to see more massive black holes more easily because they give you a louder signal. So the more scientific way of inferring this mass distribution is by plotting the mass distribution that we expect given some inference model and accounting for this observational bias. And so even if you do that, over the last couple of years, going through these gravitational wave catalogs, we'll see this feature emerging, where this is the first catalog that contains so only those 5, 6 binary black hole mergers. And just what's shown here is the more massive black hole components and the rates. And these models, or these colored lines, are different inference models that the LVK, the LIGO-Virgo-Kagra collaboration, used to infer what mass distribution it would be. So, for example, the blue is just a very simple broken power law, and model C is something more difficult with more power laws and peaks. And as we move from gravitational wave catalog 1 to 2 and different model assumptions, all the way to gravitational wave catalog 3, which was released over a year ago now in November of 2021, we see that even in all these different models, they seem to converge to agreeing that there is something going on at about 35 solar masses. So we can now, at this time, quite confidently say that there seems to be a clear feature going on at 35 solar masses. And this is one of the most, the actual location that they quote in the paper is about 34 plus or minus, +2 -4. This is one of the most robust findings that we have from the most recent gravitational wave catalogs. It's way more robust than all the findings that for now we have on spins or mass ratios, etc. But even though that this is the most robust finding we have, it is still a little bit unclear if we're actually seeing a pileup or a knee feature. So if there really is a bump before something happens, or if it just is some kind of broken thing happening. So throughout the rest of this talk, I will be referring mostly to it as a pileup, but the difference in this sense doesn't matter too much, although I will explain. Okay, so how would you form such a pileup? How would you form a feature in a mass distribution? Now, this is where I want to be very agnostic. To form any feature in a mass in the mass distribution of black holes, I think there's basically 3 different ways. And I'm going to go over these one by one throughout this talk. Starting with the most commonly assumed one, it has to do with something of how black holes are formed. So basically, it is something in the remnant mass distribution that just tells you that 35 solar mass black holes form more often than 40 solar mass black holes. And the thing that people keep on quoting is this pair-instability supernovae. So what are pair-instability supernovae? Basically, this theory has been around since the 60s, and it tells us that if you have a core mass or a star of a certain mass, and it's massive enough, you will get into a temperature pressure regime where pair production is allowed, which means that your photons are suddenly going to go around and form electron-positron pairs. This is very problematic for these stars because high mass stars are radiation pressure supported. So these photons were used to prevent collapse. And so this causes an oxygen ignition that prematurely explodes the star, leaving no remnant behind. So it's such an explosive, energetic explosion that the whole star gets ripped apart. Now, if you're a stellar core of slightly lower mass, then you might go through almost the same cycle, except that you don't get that much pair production forming, and you won't form such an explosive explosion, leading to only a partial stripping of the star or a pulse. And this is where it's the pulsational part of the pair-pulsational instability supernovae. Basically, you can go through this cycle multiple times before finally settling down, forming a core that can collapse and form a black hole. But this has very severe repercussions for the expected black hole mass that we can get from certain stars. So if you were to plot the initial mass of stars on the bottom here as a function of the final remnant mass black hole that you get, you see basically you will see there's like three regimes. The first regime is just core collapse supernovae, where the star collapses normally without any pair production. But then as you get into this regime where pair production occurs, there will be some turnover where which determines the maximum black hole mass that you're actually going to be able to get from these massive stars. Now, above this regime, we have the regime where there's complete disruption and no black hole left whatsoever. And this is what people call the pair-instability supernova gap. And it's called a gap because if you go to even higher and higher masses, at some point, photodisintegration will take over and will prevent you from forming these pair productions anyways. And so you will just disintegrate the whole star before it manages to explode. And so you get a black hole again. But I will be mostly focusing on this regime here, which is the regime, the lower edge of this pair-instability gap, which would potentially form a peak at 35 solar masses. Now, what exactly the shape is that we observe in the remnant mass distribution, so with LIGO Virgo, depends very much on the function of the pair-instability supernova remnant mass function. And what really matters is how much of a degeneracy you get here. So basically, this regime between those two dashed lines is a regime where the same carbon-oxygen core masses or multiple different carbon-oxygen core masses map to the same black hole mass, meaning that they will give you a kind of a pileup there. Whereas if you go to high enough carbon-oxygen core masses, you get the steep drop in the rate and you will get no black holes whatsoever. So in a cartoon version, a very flat pair-instability remnant mass function will lead to something that has more of a pileup before dropping down to a low rate, whereas a sharp pair-instability function, remnant mass function, will lead to something that looks a little bit more like a knee. And this knowledge has been used very extensively in binary population synthesis codes to try and model what the remnant mass distribution would look like. So here are different models used by different pair instability models that are now a little bit older, and used by Simon Stevenson using the COMPASS code, which I can very highly recommend as a very good population synthesis code. And you see that models where they assumed a very flat pair instability regime, you'll get this tiny little peak. And if you have something that's a little bit more smooth, you will get something that looks more like a knee or a bend feature. But also more recent codes, like this work from the Michele Mappelli's group in Italy and by Ioro et al., is not a Hurley-based code, but it is a population synthesis code where they also looked at the effect of using different pair instability modes to get this feature at different locations. And I want to note that all of these do get the feature near the 35, but they're all a little bit too high. So now turning back a little bit again to this implications, why does this location of this feature matter so much? Well, basically, if this feature is linked to pair instability supernovae, that means that isolated binaries cannot form any black holes that we see above this mass. So that very much determines the ratio of different formation channels. Basically, many different formation channels have been, to form merging black holes have been proposed, some coming from isolated stars, which would then not give you any black holes with masses of 40 or 50 solar masses. But there's also dynamical formation in globular clusters. And the rate of binary black hole mergers that we see above this gap directly correlates to the cluster density and the cluster mass function of these globular clusters and AGN disks, etc. But also I mentioned cosmology. So there is a very cool theory that basically if you observe a gravitational wave, you will see a luminosity distance and you will see a redshifted mass. But you won't know at what redshift the black hole merger happens unless you can link it to some redshift observation, which usually you can't. But if you know that this 35 solar mass peak is the pair instability supernovae, then you know that all of these systems should actually be 35 solar masses. Oh, I'm sorry. And so you can break the degeneracy between masses and redshift and thereby have an independent measurement of the H0 value. So there's a lot at stake here. So it would be good to know a little bit, is this prediction any robust? Is there, what does it depend on in physics-wise? And I would state happily, at least, that the pair instability supernova happening is one of the most robust predictions that we have, at least for massive stars. It is robust when over variations in the winds, metallicity, rotation, neutrino physics, and convection, as long as you just end up with a certain core mass of a carbon-oxygen core in your star. And this brings me to the only thing that, unfortunately, it's not stable or robust against, which is variations in the nuclear reaction rates. Now, this has been shown extensively by Rob Farmer in his 2019 and 2020 paper that basically says we don't really know the carbon-oxygen rate exactly because we cannot simulate stars that well. So everything on Earth cannot simulate the rates and the temperatures that we need for this carbon-oxygen to happen. So it's a theoretical rate as well. But it very much determines how the explosion will go. So if you have if you skew this carbon-oxygen rate plus 3 sigma, which is on the right of this diagram, then you will have more oxygen in your core. And so you will lead to more aggressive explosions. Whereas if you have minus 3 sigma of this rate, you will have more carbon and will have less extreme explosions, and thereby allowing you to have higher mass black holes. And so This shows both edges of the the pair-instability mass gap. And it shows also that we can push this gap up a lot, but we can't really push it down that much. But here comes the new thing. Oh, sorry. And so just to be clear, we expect a pileup to happen or the feature to appear just below where we expect this gap to be. But so last year, Mehta et al. Published a paper where they said, okay, this is really incredible, but the reaction rates that you used that they used in Farmer et al. 2019 are actually kind of outdated. They were the standard models that are used or tables that are used in MESA, but they come from 2002. And there is more updated estimates of this rate, which were done by De Boer et al. 2017, which lead to the new location of this gap to be more at the order of 60 solar masses. And even more so, Farag et al. Did an even more extensive study to really try and resolve where this gap should be by doing a large grid of simulations, both in metallicities, increasing the temporal and mass resolution, and using updated carbon alpha rates, but also exploring updated triple alpha rates, which also produce carbon. And they found that the fiducial location for the gap should be rather around 60 to 70 solar masses, which is quite far from the 35 solar masses that we were looking for. And again, you can push this down to 45 solar masses, but not much lower, even though you can push it up easily all the way to 90 to 100 solar masses. So what does this look like in a remnant mass distribution? So this is exactly something that David Hendricks, a PhD student in Surrey, is investigating. And we're looking at how much do we have to torture our models to still get something that looks like the pair-instability bump. And so what is shown here is the remnant mass distribution with at the bottom the fraction of the mass that is, or the fraction of the systems that come from pair-instability supernovae. So basically you only have to look at this region. And the orange shows the old fiducial from Farmer et al., which is already off by a couple, like by 10 solar masses, which it was before, but people were just like, it's close enough. The real fiducial from, if we follow the most recent models, it should be somewhere like this green model though, right? So what we did in this study was shift these Yocore masses that undergo pair-instability to mimic the effects that are seen in the carbon-oxygen rates. So this is much further away from the pileup here. And you would have to go all the way down, shifting 25 solar masses in the wrong direction to get anything that has a peak feature near where we see it in the data. Okay, so maybe it doesn't seem to be matching very well with the location of this pileup. One other thing that could maybe be, maybe it's not the upper edge of the pair pulsation, so maybe it's not the degeneracy in the remnant mass function, but it could be that it's the transition between core collapse and pair-instability supernova, because that happens much lower at much lower masses, and could create a degeneracy if there is some overlap where you form more massive black holes from core collapse supernovae, and then the first pulse that you get with pair-instability supernovae blows away so much mass that you're back to a lower black hole mass again. And then you would get some degeneracy at this point. Well, this is something that we actually found in our 2022 paper, serendipitously, because we were not looking at the mass distribution that much. We were mostly looking at the redshift evolution of binary black holes. But we found a peak feature at exactly this 35 solar masses. So could it be that it's just this transition between core collapse and pair-instability? Although this is hopeful, I think actually, or it looks hopeful. I think actually in reality, it's not so probable because with the gap shifting upwards, you also expect this transition to shift upwards. And the assumed difference that we have in this model is much higher than what realistic assumptions tell us. So here there's a gap of about like a first jump of about 10 solar masses, of a little bit less. And in reality, we should expect only 3 to 5 extra solar masses being lost there. Okay, so that means going back to the drawing board, what other things could be happening at 35 solar masses? How can we get some pileup? Can we maybe shift the location of the pileup with other uncertainties? And this is actually an answer to a common critique that you always hear on binary population synthesis models, saying that there's so many model uncertainties, everything is so uncertain. If you vary things up and down, all the rates change. So you can't trust anything. Maybe if we just vary things differently, things will shift. And the most common thing that I hear people or argue is, what if we just change the metallicity distribution? Because we know that, as I said all the way at the beginning, the winds that we see for black holes are very important in determining the final black hole mass that you get. And there's one uncertainty in the rate that is the uncertainty that comes from the metallicity dependent cosmic star formation distribution. So let me go on a little bit on what I mean and why this is an uncertainty. Basically, if you plot the metallicities which stars form over the age of the universe, we expect that the universe started out very metal poor and ended up pretty metal rich today, or at least the stars that are forming today will be mostly forming with high metallicities. But in reality, we don't really know what the shape of this distribution is exactly. As I mentioned, the metallicity that you assume for the birth of your stars that will form your merging black holes heavily affects the black hole mass and rates that you get, which has been shown by many people. But moreover, this function is poorly constrained, especially at the low metallicity end and high redshifts, which are most important for black hole formation. And so how do you capture this uncertainty in your models? Well, there's been many, many different ways proposed to how to do this. And typically people use galaxy scaling relations. But what we did was try and take a more pragmatic approach where we came up with a very simple, convenient analytical expression that just explains this cosmic metallicity distribution as a in function of the overall star formation rate and the cosmic metallicity distribution. And now this is nothing very complicated, but the benefit of just using an analytical function that we understand the shape of and that we know how it evolves means that we can use this function to fit to existing data, for example, to data from cosmic simulations or from observational constraints. And we can easily update it as new information becomes available, like from JWST. But most importantly, we can now do a systematic controlled experiment of the effect of this cosmic star formation history on the inferred black hole distribution. And so that's exactly what we did here, where we used as our fiducial model the TNG 100 simulation, and we fit our star formation rate function to the data from TNG. And we now vary one single aspect of our fiducial model to understand what that does to the expected behavior of the mass distribution. So we use this metallicity function in combination with population synthesis to create a mass distribution. And now we vary from this metallicity distribution one aspect at in this point, the width of the metallicity distribution at redshift 0. So that's something very much understandable. We know what the width of the metallicity distribution means. And we can do the same trick for all the different parameters that make up the shape of this star formation history, while we keep the binary physics in the background constant. So for example, here we change the redshift evolution of the metallicity distribution, or the height of the overall star formation, or the skewness of our distribution at different redshifts. And this allowed us to make one very important conclusion, or draw one very important conclusion, namely, even though indeed the rates of binary black hole mergers can vary by multiple orders of magnitude by changing this star formation distribution, the location of features that we expect do not change. And so here I'm flipping through all the different variations, and I'll flip back and forward a little bit. And I'm highlighting just one feature at the low mass end, but it doesn't really matter if any of the features that we expect are only moving up and down if we change the cosmic star formation rate, but they're not moving right and left. So this gives us some hope that the features that we see in the mass distribution really depend on the underlying binary physics that we adopt, and not so much on the cosmic star formation history. And we know that the Pair-instability should give you something, although it should happen all the way out there at 60 solar masses. Okay, so lastly, going back to the drawing board once more, we've seen, or have hopefully convinced you that based on up-to-date models, we don't expect this feature to come from Pair-instability. We don't expect to be able to just fiddle with the metallicities to move this feature around. So there's only one option left as to explaining what this 35 solar mass feature is. And that's what I call picky pairing. Basically, is there something in the formation channels that tells you that these systems like to form pairs of 35 solar mass black holes? And oh yeah, I want to shameless plug for myself that actually I'm focusing now on this high mass feature, but I'm also really have some really exciting things to say about the low mass feature at 10 solar masses, but that's not for this talk. But please feel free to ask me or shoot me an email if you want to know more about that. So what do we expect from different channels? Well, as I mentioned before, many different channels have been proposed to solve the problem of how do we form a merging binary black hole. And all of these different channels will lead to different separations and different assumptions. And unfortunately, up until today, none of these channels really have a clear prediction of why there should be a bump at 35 solar masses. So this is me calling out to all the theorists in the room. I would love to see new ideas and new explanations for what could be the origin of this peak in the mass distribution. But personally, I work a lot on isolated binary evolution, as you might have noticed by now. And so I've looked a lot about what do we expect from isolated binaries that form merging binary black holes. And so in general, you can subdivide the isolated binary channel into two main channels. One being those that lose their angular momentum and shrink their separation through common envelopes, which is called typically the common envelope channel. and one where the shrinking is done by mass transfer, but only stable mass transfer. So these are stars that go through multiple phases of mass transfer, which can shrink the orbit and finally give you emerging binary black hole. But they will lead to very different separations and thus different delay times, etc. But one very important finding, or very exciting finding, in my opinion, that we made in 2022 is that not only do these two channels expect to give you different delay times, they are also expected to give you different masses. Or more specifically, the common envelope channel is really, really bad at making high mass black holes. And you see that somewhat in this figure, where you see this is only one realization of the binary population model, but you see that the common envelope channel drops in rates after about 25-ish solar masses, and the stable mass transfer channel dominates the rate that we see there. And this is only, as I said, one variation that we explored. We explored like 30 or so variations, but I don't just believe in this because I varied a bunch of parameters in PPISN. I believe that this common envelope channel is bad at these making high mass black holes because I think we understand the physics behind it or the reasoning behind it. And so this is a bit technical, but basically, to form very massive black holes, you need very high mass stars. And these high mass stars that could form these black holes with masses of 30 or 40 something solar masses don't have very large extended envelopes. They typically stay very small, both due to wind stripping and due to enhanced rotation sometimes. They don't like to go into unstable mass transfer because they have more hot envelopes that are radiative and so contract instead of expand when they start mass transferring. And they are also less likely to survive a common envelope when they go into this common envelope eventually, because they are, again, very hot, which if they do go into a common envelope, this is more likely to lead to a stellar merger. And even in the reverse, if you form a massive black hole first and then go common envelope on the way back, it is also very unlikely due to several ways that mass accretion and works with the mass transfer, giving you only very few systems that can make it, and most of the systems just merging if they do go into a common envelope. And this is not just based on population synthesis results. This is a result that has basically been accumulating over the years from many different people who've been working on the detailed physics of common envelopes and been showing that this stability doesn't work that much like this. And so even more so, this fact that, or this result that the common envelope channel is really bad at making high mass black holes has been confirmed by multiple independent groups over the last couple of years. So it has been shown, for example, by, again, the group of Mappelli using the MOPSI code, which is a Hurley-based code, but it has also been shown by Max Briel, who used BPAS, which is not a Hurley-based code, but uses the star evolutionary code. And it's been shown by Belczynski, who uses Star Trek, which is, again, a different code. And all of these codes agree that if you go above a certain mass, the common envelope channel becomes very inefficient. And so this means, in my opinion, that if we're looking for a feature at high masses, then for sure we shouldn't be caring about what common envelopes do, but we should really be caring about what the stable mass transfer channel does. Now, someone who has been thinking about this a little bit as well is, again, Max Briel, who tried to explain, or also noted that they couldn't form this bump at 35 solar masses with pair-instability supernovae, but they did say they could form it with a combination of stable mass transfer and chemically homogeneously evolving stars. Now, there's a lot to unpack here, and I'm actually not going to spend that much time in explaining this, but it comes down to the details of what you assume for chemically homogeneously evolving stars, whether or not you get a bump there. And that brings me to my last kind of hope or exciting thing that I think has a good chance is these chemically homogeneously evolving stars, which I think are perfect candidates to maybe create a bump at 35 solar masses because they typically have high masses like this. And I want to also use this moment to promote a little bit another student that I'm working with, Katie Sharp, who, if you don't know her, is going to visit Caltech, I think, in a couple days as she's making her grad school tour. So it's very exciting. But basically, chemically homogeneously evolving stars are these theorized stars that can form very massive black holes through mixing their interior and envelope and creating pretty massive black holes. However, to date, there has been no confirmed observation of a chemically homogeneously evolving star. And so what Katie has been doing is exploring different models of chemically homogeneous evolution to see if we can explain one of the best candidates for chemical homogeneous evolution, namely HD 5980. And so these are some of the grids that she has been running looking at variations for the winds and the mixing, etc. And so the blue, what you see here, is chemically homogeneous evolving, and gray is normal evolution. Just in summary, I would say if you are excited about chemically homogeneous evolution, try and chat with Katie if she's on her visit and not too busy already. So all of that brings me back to my summary, basically where I started out with saying that I don't think the 35 solar mass bump comes from pair-instability supernovae. And that is because state-of-the-art models just don't predict the gap to be at that regime, but way higher at 60 solar masses. And we can't just move around with these things just because we are so in love with our theory that it seemed to match so nicely. And I think this has this has implications for the expected contributions from dynamical formation channels and how we can maybe use this feature to infer, use black holes as standard sirens. So I think we need a new explanation for these 30-something black holes. So the next couple of years is the perfect time to make a comeback and come up with new ideas, where I've showed that at least common envelopes are a bad candidates as they will only produce low mass black holes. And I think the strongest candidates, at least from the isolated evolution, are stable mass transfer and chemically homogeneous evolution. But again, I invite everyone to come up with new ideas, as O4 is coming out sooner, starting this May, and will run for 18 months, meaning that we'll triple or maybe even quadruple the number of black hole detections that we have, giving me a very good hope that we'll be able to really tightly constrain the location and shape of this feature, and maybe even possibly see a feature appearing at 50 solar masses. Who knows? In any case, I think it's an exciting time for theories to be around, and I hope many new papers and new ideas will come forward the next couple of years. So thank you very much, and I'd love to have some questions.
Thank you very much. Okay, if you have a question, just raise your virtual or your physical hand. Yep.
I see Sterl. I don't see the room, so I don't know if there's questions in the room.
We'll start with one in the room and then we'll go to Sterl.
This is Javier. Thanks for the talk. So, would you say that the 19 of 521, in light of this new limit, is no problem for the I suppose the challenge.
So sorry, I'm having a hard time hearing.
This heavy binary black hole 190521.
Yeah.
Then in
If
light
it's
of
a
this
problem.
updated the limits, there is no problem.
Yeah, that's a very good question. So JW 190521, if I'm not mistaken, has one of the masses is 60 solar masses, 60 something, and the other is 80 solar masses. So if you would ask my honest opinion, I would say that it's most likely an example of one second generation black hole and one first generation black hole. So this makes it significantly less difficult to produce, because now you only have to worry about merging and getting to a second generation for one of the two components, which can be done in globular clusters. That has been shown by Rodriguez and other people, and been working at these hierarchical mergers. But before, if the gap was really at 45 or 35 solar masses, then you would need at least two, sorry, my presentation is living its own life, at least two second generation black holes, or maybe even third generation, to meet up with each other. And that, I think, is basically impossible. So you would need some more exotic explanations. And so this actually alleviates some of the tension for JW 190521.
Sterl?
Yeah, so I was just wondering, a little later on, you had a plot of the number versus mass with the metallicity redshift evolution. And I was just wondering, is the mass on the
did you mean this one? Or
yeah, or the ones like that. Yeah, that one's fine. Are the masses you're plotting there rest frame masses, or are those actually observed 1 plus z times m masses, which
no? Yeah, no, here it's rest frame. So mostly I'm really looking at rest frame masses. So indeed it would look more extreme or different if you move to observed masses.
But I guess given that you have the redshift evolution, I guess the question is how much different would they look? You know, I mean, LIGO's current O3s are already the highest masses. It can be a redshift 1. So, I mean, there's some stretching of the thing. Have you tried to see how much the stretching matters for the?
Yeah, I've looked at that at some point. I don't actually have a great plot or anything to show for that, but it doesn't make too big of a difference for this high mass regime. But yeah, it would be nice to be able to actually break these degeneracies. But up until now, for those masses up to redshift 1, it's not so much a problem yet.
Because I would have thought for 04 and 05, the highest masses are preferentially, of course, at the higher redshifts, and so it'll get to be more and more of an issue. Right?
Yeah, although you will also hopefully get some systems close by. Of course, you will see the most massive ones furthest away, but we can already see 35 solar masses mergers quite nearby. So, but you're right. I think that's a good point, that we should keep that in mind, especially for the upcoming results and catalogues. Also, for now, here I'm really focusing on the redshift evolution, but for now, LIGO's official statement is also that they don't see any evidence yet for any redshift evolution, but that doesn't say much, because yeah, it really is only a few systems that are measured at higher redshifts, and they are all the higher mass ones as well. So.
Any questions? Any other questions? I had a quick one. What's the observational status of these pulsational and just normal pair-instability supernovae from optical surveys? Will Ruben find a substantial sample?
That's a very good question. So we there are a couple of candidates. I don't no, well, I'm not gonna look for the slide right now, but Sebastian Gomez had a really good candidate but it's kind of at the same stage as these chemically homogeneous evolving stars, where there's a couple of candidates, but nothing is like very securely confirmed to be a pair-instability supernovae. But there is hope to observe more of these. But how high that hope is basically depends on where you expect the mass gap to be as well. Because as you can imagine, the rate of pair-instability supernovae happening also decays if you expect that your pair-instability will only happen at higher masses. So this here you can kind of see it closely for the binary black hole merger rate. So you know that if the pair-instability would be hidden somewhere around this mass, then we expect the rate of that to be like an order or more order of magnitude or more lower in rate than if we expect it to be here. And that's just also in a large part due to the IMF. And the same is what we would expect for pair-instability supernovae. If they are starting from much higher stellar masses, then we expect them to be much more rare. And so there is hope of detecting them, but yeah, maybe not the, it's difficult.
Thanks. Any final questions? Okay, if not, then I'll thank you again on behalf of everybody else. That was great.